Welcome to the fourth installment of our series on computational electromagnetic theory. In this video, we will dive deeply into the computational methods used to solve complex electromagnetic problems, with a specific focus on how these methods apply to microwave brain imaging systems. We will start by revisiting the types of partial differential equations, PDEs, that arise from Maxwell's equations, which describe the behavior of electromagnetic fields. We will explore how these equations are derived and what they mean for electromagnetic theory and its applications. Next, we will introduce several numerical methods that are employed to solve these PDEs, focusing on boundary value problems, BVP, the Finite Element Method, FEM, and the Finite Difference Time Domain, FDTD, method. Each method has its strengths and is suited to different types of problems. BVP is often used for solving static or steady-state problems with defined boundaries. FEM is versatile for complex geometries and material properties, and FDTD is particularly powerful for time domain simulations. We will then take a closer look at the FDTD method, which has proven to be highly effective for solving time-dependent electromagnetic problems. We'll cover its formulation, including the discretization of Maxwell's equations and the time-stepping algorithms used to update the electromagnetic fields. Key considerations such as stability, accuracy, and boundary conditions will be discussed in detail. Finally, we will apply the FDTD method to a practical problem: microwave brain imaging systems. This technique uses microwaves to probe the brain, providing valuable insights into its structure and function. By implementing the FDTD method, we can simulate how microwaves interact with brain tissue, allowing us to develop and refine imaging techniques. This practical application will illustrate how advanced computational methods can address real-world challenges and enhance medical imaging technologies. By the end of this video, you will have a thorough understanding of how to apply electromagnetic computation techniques to solve complex problems, including their practical use in advancing microwave brain imaging systems. In this slide, we delve into the mathematical foundation of electromagnetic problems by exploring Maxwell's equations, which are the bedrock of classical electromagnetism. These equations describe how electric and magnetic fields interact with matter and propagate through space. When Maxwell's equations are expressed in their differential form, they naturally lead to the formulation of various partial differential equations, PDEs, each corresponding to different physical scenarios. Let's start by understanding what PDEs are. PDEs are mathematical equations that involve multiple independent variables and their partial derivatives. They are crucial for describing how physical quantities, such as electromagnetic fields, evolve in space and time. The classification of these PDEs depends on the nature of their second-order derivatives, and they are typically categorized into three types: elliptic, hyperbolic, and parabolic PDEs, each representing distinct physical phenomena. Elliptic PDEs arise in scenarios where the system is in a state of equilibrium, meaning there is no time dependency. For example, the Laplace equation and the Poisson equation, which are derived from Maxwell's equations under static conditions, are elliptic PDEs. These equations describe situations like the electric potential within a region of space due to a static charge distribution. You can see this concept illustrated on the slide, where the distribution of the electric field inside a capacitor is depicted, showing how the field remains constant over time. Hyperbolic PDEs, on the other hand, describe dynamic situations involving wave propagation. The wave equation, which can be derived from Maxwell's equations when considering electromagnetic wave propagation, is a classic hyperbolic PDE. This type of equation is crucial for understanding how electromagnetic waves travel through space at finite speeds, as illustrated on the slide with the schematic of a propagating wavefront. Hyperbolic PDEs capture the time-dependent behavior of these waves, making them essential for modeling radiation and signal transmission. By understanding how Maxwell's equations give rise to these different types of PDEs, elliptic for static fields and hyperbolic for wave propagation, we can better choose the appropriate computational methods to solve them. In this video, we will focus particularly on the numerical solution of hyperbolic PDEs because they govern the behavior of electromagnetic waves, as represented by the wave equation derived from Maxwell's equations. As demonstrated in the schematic on the slide, the mathematical model for solving electromagnetic problems, especially in dynamic scenarios, often involves using the Finite Difference Time Domain, FDTD, method. FDTD is a powerful numerical technique that allows us to simulate the time domain variation and propagation of electromagnetic fields. However, implementing FDTD requires careful consideration of numerical factors such as boundary conditions and initial values, which are critical to ensuring the accuracy and stability of the simulation. This introduction sets the stage for the deeper exploration of these concepts in the upcoming sections, where we will delve into the specifics of how FDTD can be applied to solve real-world electromagnetic problems, including those in advanced applications like microwave brain imaging systems. In this slide, we introduce the numerical methods used to solve electromagnetic problems, which typically involve partial differential equations, PDEs, governing electromagnetic fields. The process begins by converting these PDEs into linear matrix equations, as illustrated in the schematic on the left side of the slide. This conversion is accomplished using numerical techniques such as the Boundary Element Method, BEM, Finite Element Method, FEM, and Finite Difference Time Domain, FDTD, method. Each of these methods involves discretizing the model, in this case, the head model, into a mesh. In the FEM approach, the head model is divided into small volume elements, and the PDEs are reformulated into a weak form that is suitable for numerical computation. This process involves integrating the PDEs over each element to account for variations in the electromagnetic fields, resulting in the creation of local stiffness matrices. These local matrices are then assembled into a global matrix that incorporates boundary conditions and source terms, such as electric currents. Finally, this global matrix equation is solved using numerical linear algebra techniques to determine the electric potential or magnetic vector potential at each node within the mesh. In contrast, the BEM approach discretizes only the surface of the head model into boundary elements. The PDEs are transformed into boundary integral equations, simplifying the problem to a surface-based system. These integral equations are used to create a matrix system that, once solved, yields the potential on the surface of the model. From this surface potential, internal electromagnetic fields can be computed. The schematic shows the meshing process for both BEM and FEM, highlighting the discretization strategy used in each method. The slide also includes a visual representation of the different numerical methods by comparing their performance based on electrical size and material complexity, shown on the right side. In the current state-of-the-art approach for lead field estimation using BEM, the head is described using a few compartments with constant and isotropic electrical conductivity. However, BEM is limited when it comes to handling complex conductivity distributions, particularly those that are anisotropic. On the other hand, FEM and FDTD methods can accommodate arbitrary, anisotropic conductivity distributions. This capability allows these methods to consider thin and highly conductive tissues, such as bone marrow, which are typically neglected when using BEM. FDTD, in particular, is advantageous because it can incorporate arbitrary conductivity distributions and anisotropy without the need for complex meshing techniques required in FEM and BEM. This characteristic makes FDTD especially suitable for electromagnetic brain imaging, as it provides a more accurate and flexible modeling approach. In conclusion, the schematics and illustrations on this slide demonstrate why FDTD stands out as the best option for electromagnetic brain imaging, due to its ability to handle complex material properties and provide detailed insights into electromagnetic field behavior in the brain. In this slide, we delve into the application of the Finite Difference Time Domain, FDTD, method for solving electromagnetic problems, with a particular focus on how this method is implemented to simulate wave interactions within a defined computational domain. The diagram before us serves as a visual representation of the FDTD setup, where an incident electromagnetic wave encounters an object, leading to the scattering of waves in various directions. This scenario is crucial in understanding how electromagnetic fields interact with different materials, which is particularly relevant in complex applications like brain imaging. Surrounding the central object in the simulation are perfectly matched layers, PMLs, which are a key feature in FDTD simulations. These layers are strategically placed along the boundaries of the computational domain to absorb outgoing waves, thereby preventing any reflections that could distort the simulation results. The PMLs in the diagram are oriented along the x, y, and xy directions, ensuring comprehensive absorption of waves from all edges of the grid. This setup allows the FDTD simulation to accurately mimic an open space where waves can freely propagate without artificial boundary effects. The outer boundary of the simulation domain is marked as a perfect electric conductor, PEC, which acts as a reflective surface in some FDTD simulations. In this context, the PEC boundary ensures that no energy escapes the simulation domain except through the PMLs, further enhancing the accuracy of the wave interactions being modeled within the domain. An inset on the right side of the diagram provides a closer look at how the PML functions. The graph in this inset illustrates the gradual increase in conductivity within the PML, which corresponds to a decrease in the electric field as the wave penetrates deeper into the layer. This gradual absorption mechanism is crucial for preventing reflections that would otherwise interfere with the accurate simulation of wave behavior, making the PML an essential component of the FDTD method. In addition, boundary conditions are essential for accurate simulations. Absorbing boundary conditions, ABC implemented to minimize reflections at the edges of the computational domain. Traditional ABCs can introduce errors, leading to the development of perfectly matched layers, PML, by Berenger, 1994. PML absorbs outgoing waves effectively. Uniaxial PML, UPML, introduced by Gedney, 1996, improves computational efficiency, especially for lossy media. Perfectly electric conductor, PEC, and perfectly magnetic conductor, PMC, boundary conditions. PEC conditions set E to 0 on metallic surfaces, while PMC conditions set H to 0 on magnetic surfaces. This slide highlights the numerical approach of the FDTD method, which is crucial for simulating the propagation of electromagnetic waves through complex environments like the human head. We begin by revisiting Maxwell's core equations, which are fundamental to understanding the behavior of electric and magnetic fields. Gauss's law for electricity describes how electric charges generate electric fields. Gauss's law for magnetism asserts that there are no magnetic monopoles and that magnetic field lines are continuous. Faraday's law of induction explains how a time-varying magnetic field induces an electric field, and Ampere's law, with Maxwell's correction, details how a time-varying electric field or an electric current generates a magnetic field. These equations provide the theoretical foundation for our numerical simulation. To discretize Maxwell's curl equations, we use a second-order finite difference approximation within the FDTD method, which involves discretizing both time and space to capture the dynamic behavior of electric and magnetic fields. We employ E's grid, a crucial framework in FDTD, where electric field components E are computed at integer time steps, and magnetic field components H are calculated at half-time steps. This staggered arrangement minimizes phase errors and ensures accuracy. Specifically, X, EY, and EZ are defined at primary grid points, while HX, high, and Hertz are defined at secondary grid points. Each E component is surrounded by 4 adjacent H components, and vice versa. For example, at grid location I+1/2, J, K, the X is influenced by adjacent high and Hertz components. The spatial domain is divided into a grid with increments delta X, delta Y, and delta Z in the X, Y, and Z directions, respectively, while time is divided into increments delta T. We use the leapfrog algorithm, as proposed by Hussein and Seeback, 1996, to iteratively update the electric and magnetic field components based on Maxwell's equations. This algorithm updates fields at alternating time steps with half-step spatial offsets, ensuring a more accurate resolution of the fields within each grid cell by slightly offsetting the phases of field components. To maintain numerical stability, the FDTD method adheres to the Courant-Friedrichs-Lewy (CFL) criterion. The time step delta t must satisfy the CFL condition, which depends on the spatial step sizes delta x, delta y, delta z, and the maximum speed of electromagnetic waves in the medium C max. This criterion ensures the time step is small enough to accurately capture field propagation without introducing numerical instability. It's important to note that reducing the mesh step size by a factor of 2 increases memory requirements by a factor of 8 and computation time by a factor of 16, highlighting the need to balance accuracy with computational resources. Note that accurate gridding is crucial for effective simulation. For uniform and straight geometries, Yee's grid is applied by discretizing them into rectangular cells. However, for non-uniform or curved geometries, this method may introduce errors due to misalignment. For handling non-uniform geometries, 3 approaches are considered. First, shifting the geometry may lead to errors due to misalignment. Second, minimizing cell size requires more memory and computational power but provides finer resolution. And third, non-uniform cells, staircasing method. This approach approximates curved geometries with staircase cells, offering a flexible transition between boundaries while reducing memory and computational requirements. By utilizing the FDTD method with careful spatial and temporal discretization, boundary condition application, and gridding strategies, we can accurately simulate electromagnetic wave propagation in complex environments such as the human head. This approach ensures that both the electric and magnetic fields are dynamically and realistically modeled, providing valuable insights into their interactions within intricate structures. Finally, to demonstrate the correct implementation of these principles, we simulated wave propagation using a Gaussian waveform as the source. This example, involving ultra-wideband source excitation in the FDTD medium, illustrates the wave propagation through the medium and its absorption at the boundaries. In this slide, we explore the application of the FDTD method for simulating electromagnetic interactions within a human head, as represented by the voxel-based phantom displayed on the right-hand side. The left-hand first image illustrates a perspective view of a human head, discretized into a grid of voxels, which serves as the central object within the FDTD simulation medium. This voxel-based approach allows for highly detailed modeling of the head's complex anatomical structures, providing an accurate representation of how electromagnetic fields propagate through different tissues. The voxel-based phantom ensures that the variations in tissue properties, such as permittivity and conductivity, are accurately captured, allowing the simulation to model how electromagnetic waves scatter and absorb within the different tissues of the head. This is particularly crucial for applications like brain imaging, where precise knowledge of field distribution is essential. As mentioned earlier, the simulation domain is surrounded by PMLs to absorb outgoing waves and prevent reflections that could affect the accuracy of the simulation. The integration of the human head model into this domain allows for a realistic simulation of electromagnetic wave interactions in a controlled environment, where the FDTD method can compute the field's behavior over time. On the right side of the image, the voxel-based phantom image is represented in the FDTD grid form. This high-resolution model is essential for accurately predicting how electromagnetic waves interact with different tissues, contributing to more effective imaging and analysis. In the right side of the slide, the generic form of microwave imaging system is demonstrated, including the array of the antennas surround the head phantom. The combination of the FDTD method with a detailed voxel-based human head phantom provides a powerful tool for simulating and analyzing electromagnetic fields in biomedical applications. This setup allows for precise modeling of wave propagation and interaction within the human head, offering valuable insights for applications such as brain imaging, where understanding the behavior of electromagnetic fields within complex tissue structures is crucial. In general, when an incident electromagnetic wave encounters biological tissue, it is divided into several components: reflection, scattering, absorption, and transmission. The accurate calculation of these components is crucial for simulating and understanding the interactions within biological tissues. Several methods exist to model these interactions based on the tissue's permittivity, permeability, and conductivity. Furthermore, the slide discusses the dielectric properties of tissues in different conditions, such as ischemic and hemorrhagic strokes. The dielectric properties, including permittivity and conductivity, vary significantly between these conditions, influencing how electromagnetic waves interact with the tissues. To ensure the accuracy of the FDTD simulation, the computational domain is surrounded by PMLs, which absorb outgoing waves and prevent reflections that could otherwise distort the results. This allows for a more realistic simulation environment, where electromagnetic interactions can be studied in detail. Additionally, the simulation results of attenuation of the electromagnetic wave in different tissues layer, which includes a comprehensive set of voxels that represent various tissue types, such as skin, fat, bone, gray matter, and white matter, were demonstrated. The voxel model is crucial for developing accurate brain microwave imaging systems for stroke detection, as it provides detailed geometrical information about the human head. At the bottom side of the slide, the dielectric properties of these tissues demonstrated, which are dispersive, meaning they vary with frequency, which is accurately captured using the fourth Kolkol equation in the simulations. This level of detail is essential for designing and implementing the hardware and software components of brain imaging systems, including antenna elements and image reconstruction algorithms. This slide presents the extracted results from an FDTD simulation of a generic microwave imaging system. A key advantage of time domain solvers like FDTD is their ability to animate the entire process of wave launching, propagation, reflection, and scattering. However, for brevity, only a snapshot of the fields at the 2000th time step is shown. The left side illustrates wave propagation within the phantom model. Here, a portion of the launched wave is seen to have coupled into the brain matter, predominantly traveling along the x-axis through the brain. In addition, the electric field component EZ is plotted as a function of time. Notably, at around the 2400th time step, distortion in the waveforms becomes evident. In this instance, no waveform distortion is observed, however, a slight but noticeable phase shift occurs around the 2000th time step.
The middle column displays the normalized induced currents for different operating frequencies: 1 GHz, 2.5 GHz, and 4 GHz. These results are crucial for understanding the interaction of electromagnetic waves with different tissue types at various frequencies. On the right side of the slide, the specific absorption rate, SAR, distribution is shown. SAR is a critical measure for ensuring the safety of the human body against harmful radiation. Since the proposed antenna is positioned near the head model, calculating and analyzing the SAR is essential. The input power to the antenna is 1 milliwatt, with only one antenna acting as the transmitter at any given time. The SAR must comply with the IEEE public radiation exposure limit of 1.6 W per kilogram. Additionally, the slide presents sample scattering parameters, including reflected loss and transmission loss. These parameters are vital for the inverse scattering algorithm used in brain image reconstruction, which will be discussed in detail in the subsequent playlist on inverse electromagnetic problems.